All right. Let me just set up things here a bit more. Good. Where were we? We were talking about stability of fixed points. Remember the big plan that we have, which will by no means be complete by the end of the semester, but that's sort of the ultimate goal of dynamical systems, to understand dynamics in the phase space, starting from simpler things and moving to complicated things. And the idea is to have a geometric view on it. And the simplest players in this picture are fixed points. And we've been discussing the fact that fixed points are, to be at a fixed point is a very low likelihood event because it's just 1 point. Why would you exactly be there? In reality, there are always perturbations. So fixed points are really important because of their impact on their neighborhood. What sort of impact do they exert on nearby trajectories? Do they keep them? Do they repel them? Is there a mixture of behaviors? So that brought us naturally to the concept of stability of fixed points. We had various definitions: Lyapunov stability, asymptotic stability. But then at the end of the day, you want to have a way to determine the stability of your fixed point. The easiest way, when it's available to you, is linearization, which basically take the Jacobian of the right-hand side of the differential equation at the fixed point. Now, that's good. And we had various ways of various criteria, simplest being, the most important being that all the real parts of the eigenvalues of the linearization are negative. Then you have an asymptotically stable fixed point. Now, that brought us to the question, can we, however, solve this problem in some sense symbolically without really evaluating the Jacobian? Can we have explicit analytic criteria rather than brute force always linearizing at a fixed point, having to plug in all our system parameters, even the design parameters that we would like to keep open and vary, having to evaluate them and then calculate the eigenvalues? Or can we perhaps, without solving for the eigenvalues, say something about the stability? And a great classic criterion is the Routh-Hurwitz criterion, which I discussed last time. And let me just quickly review what that was. It's a sufficient and necessary criterion. And again, I told you about the ETH connection with this criterion. And the subject of the criterion is the characteristic polynomial of the linearization. But in fact, you can just state this as a general fact, general result for polynomials, but it's so specifically geared towards a feature of those polynomials that its real use is really stability theory. So if you have a polynomial like this, think of this as the characteristic equation of the linearization with the Jacobian unevaluated. So these could actually just be symbolic expressions for the entries of the Jacobian. They don't have to be numbers. Okay, that's the big strength of this criterion. And this comes from a characteristic equation where A is the linearization, the matrix of the linearization. So assume that A naught is bigger than 0. If not, you can multiply the whole polynomial by -1 to achieve that. And if you find that you cannot even achieve it that way, that the only way that can happen is that A naught is 0, but the minute A naught is 0, you should know that the linearization is already inconclusive, because when this term is out, then lambda can be factored out from the characteristic equation. So lambda equals 0 is an eigenvalue. So you have a critical case in which linearization is inconclusive anyway. So why waste time on the remaining eigenvalues? So assuming that it's non-zero, you can always make it positive. If need be, you multiply by -1. And then you define a sequence of determinants. D naught is just A naught itself. D1 is A1. So far, nothing fancy. But then D2, you take A1 and A2. And to the left of the first entry, you write down the lower order coefficients until you run out of them. And to the right, sorry, and to the left, you write down the higher order coefficients until you run out of them. There's only one for these both of these roles. The same rule for D3, you write down A1, A2, A3, and start listing the lower order coefficients to the left until you run out of them. If you still need more to complete a 3x3 matrix, you start writing zeros. And to the left of them, you start listing the higher order coefficients until you have them, and you run out of them, you start writing zeros. This way you can build a sequence running from A0, which is D0, to Dn. So this is a total of n plus 1 expressions in the end. Still, you don't need numbers here, because the issue is you really can't solve this polynomial numerically when these are symbols, unless it's of order 2 or with Cardano, order 3, but it's messy. With order 4 or order 5, you're out of ideas. If these contain parameters, you just don't know how to look for the zeros, because Newton's method or any other root finder method cannot operate on symbolic expressions, right? So you do have to plug in all your parameters and constants. So you're not going to get some sort of general understanding in your parameter space. However, for what I'm describing right now, that's not necessary. You don't have to plug in numbers here. These can remain symbolic expressions. Okay? That's the big value of this. You never have to do any numerics. Just evaluate these determinants, which is instantaneous. Then the criterion says that all real parts are, for all the roots, are 0 precisely when all these di's are positive. Remember, the first one had to be positive by construction, and all the rest also need to be positive. This is all, the latter part is also a necessary condition. So if you don't have, you also have a necessary condition that if just by inspection, if you find that these coefficients have different signs, then you cannot have asymptotic stability for sure. So it's a quick check. So why waste time when evaluating the polynomials if some of these are just inherently different in sign than others? Okay, so this is where I was. Any questions on this? If not, I wanted to write out the cubic case, because, for the quadratic case, we surely have the quadratic formula. So you could simply write out the roots symbolically for this equation when n is 2, right? You just solve it, you write down the solution formula for the quadratic formula, and then you get a symbolic expression for the 2 eigenvalues, and you simply require the real parts to be less than 0. That gives you an inequality, right? Example 2 would be in this area, I think. Did I have example 1? Well, I must have had at some point, but example 11, sorry. So it's not Roman 2, but example 11, apparently, in my notes. So what happens in the first case, when we cannot on our own, without the Routh-Hurwitz, could not really efficiently evaluate the stability symbolically. So n equals 3. So when n equals 3, the polynomial you have is a3 lambda cubed plus a2 lambda squared plus a1 lambda plus a0 equals 0. This is your characteristic equation, right? So these Routh-Hurwitz conditions, in this case, what's their form? The first one is always a0 has to be positive. Again, if that's not the case, just multiply the polynomial by -1. But let me actually write it in the way that I have. So I actually call this to be d0, okay? And the next one is d1, and remember that's just a1. So a1 also has to be positive in this case. So the first non-trivial condition is d2, which is the determinant of this matrix that I had here written out, which is a1, a2 minus a0, a3. Okay, and d3, and in the case of n equals 3, that's the last one I have to deal with. So these expressions are the same for any order, but what will change is the number of those that I have to pay attention to. So if this was a second order equation and I don't remember the quadratic formula, I could stop here and I could just require these inequalities, and then I don't have to know the quadratic formula. If it's a cubic equation, then you will stop here. If a fourth order equation, you stop here, but the expressions are the same. So in the case of the cubic formula, I can take this determinant expediently. See, I can just work this out, say a3 A1, A2 minus A0, A3. And since this is all I have at order 3, I don't have high order coefficients. In that case, A4 is 0 and A5 is also 0, okay, in my present case. So the only contribution to the determinant would be, I can calculate the determinant as A3 times A1, A2 minus A0, A3. So this will be A3 times A1, A2 minus A0, A3. Again, this expression would then start changing. I was incorrect when I said that they wouldn't change. They do change. They start changing when I don't have higher order terms. Their core is the same. But if I had A4 and A5, then of course the determinant D3 wouldn't be this simple, clearly. Okay, but that's it. Basically, the criterion is the Hurwitz criterion is that the DIs have to be larger than 0. I goes from 1 to 3. Okay, so what does that tell me? So it tells me that A0 must be positive, A1 must be positive, this D2 must be positive, and D3 must always be, or must also be positive. And if you look at these, then not all conditions in this case are independent, because once I well, that's not the right way. So let me just say that the conditions you can set up implications instead of taking the conditions on face value, because once you have assured that D2 is positive, right? Then since D3 is the product of A3 and D2, okay, what D3 really amounts to, given if this is satisfied, is this satisfied, and this is satisfied, then what D3 bigger than 0 really amounts to is A3 bigger than 0, right? So if you did do the inspection at the beginning to make sure that you're not doing unnecessary work, and you checked whether the coefficients had the same sign, then you already had to have A3 bigger than 0. So that should be a given. Have you checked anything? Because that's already part of the necessary condition. Okay. This is also, this is part of the necessary condition. This is also part of the necessary condition. And this is also part of the necessary condition at the beginning. So once you have done your homework and you check the necessary condition, you have already checked these, and the only non-trivial condition that arises here is the D2 bigger than 0. You could also say that all right, but the necessary condition also asked me to check whether A2 is bigger than 0 or not, and that seems to not play a role here, right? So why did I need to check that? Well, if you take a closer look, if A2 were negative, look at D2. A0 has to be positive. We've seen that. A3 has to be positive. So this number here is negative. But also we have concluded that A1 has to be positive from here. So you have a positive number. This is altogether negative. So if A2 was negative, then surely this would be negative and fail. So this just kind of nicely shows after the fact a specific case, the proof, if you will, for the cubic case that A2 bigger than 0 is in fact, as generally stated, even in this case, where in a cubic case, one can see that it's necessary. So no. S2 bigger than 0 is also necessary. As stated. For asymptotic stability. Once again, why? Because if that wasn't the case, then or say A2 is 0, then this is already negative. So we have a problem. If A2 is negative, non-zero, then we still have a problem because A1, A2 is negative. So altogether, this is negative. So we don't really have a chance, right? So then the only non-trivial condition in the 3D or the order 3 case is this one. So this is the single non-trivial condition. I say non-trivial because you have checked the signs being positive already. Otherwise, you wouldn't even start this whole thing. So this is to be satisfied for real parts lambda I less than 0 for all I. Okay. But again, those for all i's are not a whole lot, right? Because it's just 3. This is a 3-dimensional example. Okay, so it's as simple as that, and just see the value of it, that you don't have to solve this equation numerically. You don't have to go through the complexity of applying Cardano's formulas, which, make no mistake, will give you cubic roots and complex numbers and everything. Basically, just check this inequality. And if all the coefficients had the same positive sign, and this inequality holds, then you have asymptotic stability. So each, and you're talking, if this is now if you think of this as a, A0 and A1 are generally not independent parameters, but let's just assume for a second that all these AIs are independent parameters for a second in your dynamical system, then you have a parameter space which is 4-dimensional, okay? And each and every one of these conditions, inequalities, defines an open set, which is to the right or to the left, so to speak, locally from a dividing surface. Say A0 equals 0 is one of those surfaces, and one side of the parameter space that falls on one side of that is okay for asymptotic stability. The other one isn't, okay? So you use these 4 equations dividing 4 surfaces in that case to find an open set in the parameter space. These are the boundaries of that open set over which you have asymptotic stability. If you don't have such an open set, because some of these conditions are mutually exclusive, you can't have all 3 or 4 satisfied at the same time, then you simply have no chance for asymptotic stability, okay? Now, in reality, in real problems, these A0 and A1, these polynomial coefficients are functions of other parameters. So basically, your parameter space may be higher dimensional or lower dimensional. You might just end up having ultimately a 2-dimensional parameter space, and all your coefficients depend on those 2 parameters. Then what you are faced with here is that these individual conditions are violated along curves. So you will be plotting 4 different curves, and you will think of them as, if all goes well, you will think of the region that they enclose as boundaries, and whatever that region is, where all these inequalities are satisfied, that's your region of stability. So that's conceptually the approach. So what I'd like to do is do a famous example, which many consider the first example of control theory, the birth of control theory, which I already mentioned last time. And here's the example. In order to save time, I'm just going to go through my notes, and you will see this, and I'll copy these in. So it's about in some sense, the heart of the steam engine. So this was first, it's a controller, and it's called the centrifugal governor or centrifugal regulator. It's this device here. And this was originally invented, as I understand, for mills in the 1700s, very early, so before the steam engines. But then it was adapted by James Watt to the steam engine in 1788. And this is what makes the steam engine work. Otherwise, it would keep blowing up or stopping, okay? So what does this device do exactly, this centrifugal governor? The steam engine is actually not shown in this picture, but it's spinning somewhere, okay? And with a transmission, with a set of gears, you take some of that, you transmit some of that rotation into this device, which is basically a rotating pendulum. And this has been one of your homework problems, the rotating pendulum. So this shaft, this spindle is rotating. And again, its speed, its angular velocity is generally not the angular velocity of the rotating shaft of the speed engine, but rather there's a gear ratio between the two. But nevertheless, they are intertwined with that ratio. So this is rotating. And there's a sleeve here, which is able to slide up and down, and attached to that are these two weights. Say their weight is m divided by 2, m divided by 2. And if the speed of rotation goes up for this rotating pendulum, then because just the sort of the popular explanation is that the centrifugal force will cause these masses to move outwards. Because of the constraint, they can only do so in a circular orbit, which is not that important. What's important as a result of that, so two things will happen. This angle phi will increase, okay? But also the way this is constructed, that outward motion will cause this arm to move here. So if you spin faster, these move upwards, and then if these move upwards, then this arm will go up, if I got this right. And then if that arm goes up, then the other side it goes down and starts shutting off the valve of the steam engine. So the faster you spin, the less steam you're gonna get. Okay, so that prevents the engine really from blowing up because it's really gaining speed. Then this is a natural mechanism to basically dampen the flow of the incoming stream, right? Likewise, when it's moving too slowly, then these will be descending more than they should. And when they are descending, there's an opening up of the valve here. So basically the engine gets from the cylinder, it reaches more power. So this is a simple control mechanism that obviously needs to be tuned, but it was a major invention and really, I think this is credited, I say here, as a major factor in the Industrial Revolution, because this just made steam engines work, and the steam engines could be left even quasi unsupervised. The person didn't have to stand there and govern the flow of steam constantly. And this basically stabilized the steam engines. And there was a major, major advance. And things are going well, but people then started making design changes. And even though technology was improving as a result of having steam engines, at some point the steam engines have become unreliable. And this is well documented. And people didn't understand why that was happening, because the technology, the manufacturing of steam engines has clearly improved. They were more advanced, there was more experience about them, but somehow the controller has started failing and made the steam engines unreliable. And there was no systematic way to analyze this until actually quite some time later, but Vishnegradsky was a Russian mathematician, tried to understand the root cause, and his study was basically the first that people credit as a first study in control theory, trying to understand how the controller should be designed, because before that it was just whatever I have given you here, and people, I'm sure they were experimenting with parameters. One combination worked, they left it at that, but then that very same combination started not working later on. So he wanted to look at what's going on here. So he actually wrote down the equations of motion for this cause, and this is the equation of motion that was featured or has been featured in your homework. I still call them homework. These are just problem sets. We used to give them out as homeworks, but they're just problem sets. You don't have to turn them in, but they're being discussed in the problem session. So this is the equation of a rotating pendulum, M is the mass, the total mass is M, and because you have M half here, this length is L, is the cartoon of the problem, and this angle is phi here, and the whole apparatus is rotating, and its angular velocity is theta dot. Okay, so when you go through the moves and derive the equation of motion, then you have the inertia term here. This is the moment of inertia appropriately for the angular acceleration. And here you have a viscous damping factor, which I cannot show here, but it's responsible. It models essentially everything, all the contacts here. And it depends on how smooth the surfaces are. And this is responsible for the rotating part. You have, again, the mass, you have length squared, you have the constant of gravity. And here comes the actual speed in, which is the angular velocity of the rotation of the spindle. And that's a theta dot squared. It appears the second power. Again, that's the equation in the problem set, and cosine phi. And the whole thing multiplies sine phi. So I'm not going to rewrite this equation of motion, just accept that. And let's just somehow bring in the engine, because by itself, this only is the equation of motion for the regulator. So how does that relate to the actual steam engine, the rest of the story? So if omega is the angular velocity of the actual steam engine, which is spinning somewhere, remember, generally speaking, that is not the same angular velocity at which the regulator operates, but you use some gear ratio there, which would be n, and therefore you multiply with n the angular velocity of the steam engine, then you get the angular velocity of the regulator. This just serves to bring in the dependence of this motion. The only way this motion really depends on the steam engine itself is through this omega. Now, omega is not constant because there are various things happening. First of all, the regulator is typically active, so the steam intake is changing. Can you get more steam? The engine will spin faster. You get less steam, it'll be slower, right? But also things depend on the load, how much the machine, how much load is acting on the spin engine. So steam engine. So what's the equation for the steam engine? So something similar. The steam engine, let's just model it mechanically as a spinning disk. And that turns out to be enough. So this is the moment of inertia of the engine. And this would be the angular acceleration of the engine. So this is Newton's law, right? Newton's law in the angular form. So not the linear momentum principle, but the angular momentum principle. What does that say? It says that if you properly, apply this with respect to the center of mass, not another point, then with respect to the center of mass, then it's basically the moment of inertia tensor with respect to the center of mass, but this is just a single scalar at this point, times the only component of the angular velocity that we're modeling, which is a single component, and differentiated with respect to time. Okay, so moment of inertia times angular acceleration equals is the resultant torque. Now, what is the resultant torque? On the one hand, something is driving the steam engine, the torque coming from the steam intake, but at the same time, there's a load on the engine. It's not just spinning idle, but on the other end of the shaft, there's a load, there's a torque that's resisting the movement. So that's the load, right? And for simplicity, assume that the load is constant. Even if it changes, then in most applications, it changes very slowly. So it's quasi-static, right? So let's not make things complicated. The load is constant. And what's really varying here is the driving torque due to the steam intake. And that's varying because of you, because you have installed this controller. So let's understand how that P1 varies. So P1, there's some nominal working point, some value of, at some operating point. This is where you would like to be, because that's how you calibrated your engine. That's how you designed it. Okay. So therefore, that in an ideal world, this would be actually just P star minus P, and the difference of the two would be responsible for the resultant spinning of the engine, okay? But that's in an ideal world. So there are constant perturbations to the engine. The load, for instance, may have peaks in it. Somebody kicks the engine, various different things. So you're never at that. You're not typically not at that equilibrium position. Plus, in your modeling, you have made slight or not so slight approximations. There's unevenness, bumps, whatever. So you're not exactly there, although you could. So but then you apply to this torque, you apply a control force. So this is a gain term designed to magnify this difference in the cosines. So why the difference in the cosines? So this is the angle here, phi. So what's going to matter here for the purposes, for the point of view of a computer, is the change in the height, right? Because this sleeve, the motion of the sleeve is actually directly related to the change in the height of these masses. So what happens here is that of course this is some coefficient that will take this change in the height and translate it, if you will, with an appropriate amplification factor to the change in the driving torque. But if phi goes up, so that means that this ball is going up, okay? And if phi goes up, then the cosine phi increases. Cosine phi decreases relative to cosine phi star, right? So this becomes negative. So if things are really spinning up, then there will be a negative change to the torque P1. Likewise, if phi is decreasing, then this is larger, relative to phi star, the desired operating point, then this will be positive and you have the opposite effect. So it's basically a feedback controller, as the simple linear one. Of course, that's not necessarily how James Watt thought about it. Just he understood the physics, or people who developed this for mills. And then, but that's the first order model of that. And here phi star is the desired, the operating point is phi star when you have a particular angle. Here phi equals phi star, and that generates a particular driving torque. Okay, and this then describes how you deviate from that. And if you then take this expression, plug it into this second equation, then you can pull out the term that really depends on phi. So that's k times cosine phi, and take all the remaining other terms, because this is a constant. This is also a constant, and this is also a constant. So just group them together and call it P naught. So that P naught is all the constants taken together. So the actual evolutionary part is here, phi. And this is then the coupling between the two equations, right? Because the other equation was for phi. So we now have two differential equations. One of them is second order. The other one is first order. So importantly, what do we want? So what we want is stable operation. So physically what we want is, first of all, a steady state for this system. And we want it to be stable, but not just stable, but asymptotically stable. Why not just stable? Because stability by itself also would allow for oscillations. And again, that would be detrimental to this apparatus if it kept hitting itself, or these oscillations clearly would disturb the operation. That's not what you want. Ultimately, the material will get tired. This is not beneficial. You want asymptotic stability. So it means decaying oscillations, and then until you hit the next bump and then the next perturbations. So basically you want asymptotically stable fixed points. So in order for us to make progress towards that, we have to write out a first order dynamical system. So one of these is second order. So we do the usual trick. We introduce a new variable. The angular velocity we call psi. And then by definition, therefore, the first equation of this dynamical system will be just this definition, which is phi dot equals psi. And the second one will be psi double dot, but psi dot, sorry. And that's just phi double dot. So that equation I get by going here dividing this equation by m, right? And then I get an equation for phi double dot from here. So all I need to do is to divide by m. So that's my second equation here. See the division by m. And whenever I see phi dot in this equation, I'll just plug in psi, okay? And my third dynamic variable is omega that appears here. And for that one, I have this equation, which I have simply obtained from this one. I just rewrote it after dividing by j. So this is a three-dimensional autonomous dynamical system, hopefully capturing the essence of this control circuit. And it's definitely nonlinear. So what's our first, and this is the three-dimensional variable here. So this is in, I could say R3, but really two of these variables are angular. So if I really want to be precise, then the phase space is S1 cross S1 cross R, because omega is not restricted. So first I want to see what the operating point comes out to be. So what's the operating point? The operating point would be a fixed point. So that means that all these dynamical variables, such as the rate of spinning, as well as the position of the mass is constant. So that fixed point I get by equating the right-hand side with 0. So this is what sort of symbolically, if I call this whole right-hand side F, then I'm looking for fixed points. X naught is a three-dimensional vectors, have a phi component, psi component, omega component, such that the right-hand side vanishes, right? Now the first equation, so this whole thing needs to vanish. So therefore the first components must vanish. So that means that psi has to be 0 on the equilibrium point, which makes sense. Psi is just the derivative of phi dot, so phi should not be changing. Okay, that's constant. When I solve for the second, well, the next one, it's easier to jump to the third one, because only here do I have a variable, cosine phi. So I equate this with 0, then I get this relation here. No, sorry, I get this relation here from the third one. And from the second one, since psi is 0, then this term is out. So this whole thing has to be 0. Now, one solution to this being 0 is, of course, sine phi being 0. But sine phi equals 0 is not something that I can physically realize, because it's basically my model would fail at that point, because these are sizable balls. So as they approach this limit, at some point, I'm not going to be able to push the phi angle completely to 0. So I'm ignoring that bit in the modeling, and I just assume that I have a reasonable distance from there. So my model would actually break down, and it's also not physical, because the physical system, I can't push these balls against each other. They are rigid balls, right? And they would also have to penetrate the spindles. That doesn't work. So the only that's not physical. The model is actually not correct there. So it's only phi non-zero solutions that I allow. And when I do that, again, this has to be 0 because psi vanishes, and this whole thing has to be 0. But sine phi cannot be 0, so this has to be 0. And that's the second equation. And what you see here now is psi naught, omega naught, and phi naught. These are nonlinear equations for the coordinates of the steady state. And again, this is ignored. Well, you can non-dimensionalize. For simplicity, I just set L equal to 1, but the proper way to proceed would be at this point is really to non-dimensionalize all variables to reach general conclusions. But for simplicity, I just take everything to be non-dimensional to begin with. And I set L equal to 1 to have one less of these parameters to worry about. So so I do have now, this defines the fixed point. Next thing, I need to linearize. So I linearize at this fixed point, which means I think of this equation again as a three-dimensional set of ODEs. And the new variable y, as usual, will be the difference of x minus x naught, right? Where x naught is the steady state, the fixed point. So we know how to do that. We don't have to go through the usual, well, y squared, Taylor expansion, let's make these small. This is just, linearization is simply a procedure that does nothing else but replaces a nonlinear system with this Jacobian at the fixed point times a small displacement, right? And that's, we know what that is. And we also know how to compute that Jacobian. That Jacobian, again, the Jacobian on the right-hand side. So the Jacobian needs to be taken with respect to these variables. When I do that to the first row of the equation, it only has a dependence on size. So I will get 2 zeros. But again, this is the order of the variables I have chosen for this calculation. So I will only have a non-zero derivative with respect to psi. That's in fact 1. And it doesn't matter where I take this Jacobian. Then I take the second equation and take first the derivative with respect to phi. Then I take the derivative with respect to psi, and then with respect to omega. And after taking these derivatives, I actually plug in the coordinates of the fixed point. That gives me this row first, and finally gives me that. There's a bit of algebra involved in calculating these, but you probably believe that. This one is easy to check, right? Hopefully, because I differentiate the last row of the equation with respect to the first variable, that's phi. So the derivative of cosine phi is minus sine phi, okay? And from these equations, when I plug that in, what I should be getting is minus k over j, which surprises me though, because the equilibrium for it's sine phi, so minus sine phi. Let's see from here. I think I'm missing here just formally sine phi naught. And I don't think it's 1 because it's not 2, right? So that looks like a typo there. Okay. Once I then what do I do next? Well, I have the characteristic equation in principle, and I would need to, this is a classic example in which I really want to leave things as general as possible. Look, these are all symbolic coefficients for the matrix, except for this one. This is a numerical value, which is 1. But all the rest contain important parameters in the system, and I would like to keep them as long as possible without committing to giving values to them, because I'd like to understand what's going on. Can I identify perhaps the main reason why the steam engines have started or did start acting up after a while? So if I write out this characteristic equation, then I get first lambda cubed, and then b over m lambda squared, this expression multiplying lambda, and this expression as a constant, and this is equal to 0. I'm skipping the algebra here, but I think this is with high likelihood this is accurate, because I think I checked the source where I was this. I forgot exactly where this is from, but I also checked the calculation myself a few times. I didn't notice this typo here. So this is a cubic equation and with a bunch of parameters. Okay, and instead of trying to solve it numerically to decide about asymptotic stability, this is the type of case in which I'd love to use the Routh-Hurwitz criterion to see when the fixed point is asymptotically stable. So remember, the necessary condition for that to happen is that I need to have the same sign for all coefficients. Now, this coefficient has a positive sign because it's 1 to begin with. This coefficient is positive physically because B is a damping factor, so it has to be positive. The mass is positive. G over L is positive. Sine squared phi naught is positive and not even negative. And cosine phi naught is also positive because we are in this range of angles between 0 and pi over 2. Okay, so far these are all positive, so that looks good. And I just need to look at the last one. G over L is positive physically. 2k also, what was that k there? I forgot the k. Okay, it was here. Sorry, that was the gain. That's also positive. Otherwise, my control system would not work. That's the way, then it would be, you know, it would be negative feedback. What is it? Positive feedback. So depending on what you consider it, so it would cause instability. This is again positive, and everything else is also positive because omega naught was just the magnitude. Okay, so all of them are positive. So the necessary conditions are always satisfied. Again, and an important thing in that was that I'm working in this range of angles, right? Because if the angle is happens to be here, then surely I have instability. But I'm envisioning small perturbations of this position. Okay, so my angles are between 0 and pi over 2. And not only that, I think it's not so much the perturbations, but the operating point, I should say, is somewhere down here, the fixed point. So that's positive. So everything else is positive. So the necessary conditions are satisfied. So in principle, this can well be stable. And this is also sort of a reality check, because we do know that when properly designed, the steam engine is stable. It was asymptotically stable for a long time. If we got a contradiction here now, then there would be already a problem. So there has to be, the necessary condition has to be satisfied for this construct. But the devil is in the details. So why did it lose asymptotic stability at some point in history? So let's move on to the actual Ralph-Hurwitz criteria. So remember, this is the cubic case that I worked out here in detail. So you have to have the necessary conditions satisfied, which is all of these coefficients must be positive. And the only other condition, in fact, when those are satisfied, is the DI has to be larger than, I'm sorry, that's where was I'm pointing at the wrong place. It was this. So these are satisfied, and also A2 is larger than 0. So this is really what we're after, that single condition. So like I said, I'm just writing these out here again, that these are satisfied. That's why you have the checks here. But D2 being positive is non-trivial to satisfy. So when you write it out for this particular characteristic equation, you get this inequality. And again, I just say here again that the D3 bigger than or equal to 0 is already equivalent to D2 bigger than or equal to 0. So the only condition is really that you need to satisfy is that this has to be positive. So if you do some simplification, that there's things to cross out here, for instance, G over L, right? And then sine squared phi naught cancels out and all that. And you also then use the expression for phi naught, because we have various expressions here. You know, there's a relationship between omega naught and cosine phi naught at the equilibrium point. So if you plug in these relationships into this inequality, and it turns out that the only condition that you get is this. So Bj, being damping factor times moment of inertia divided by mass, must be larger than 2 times P naught. What was P naught? To step back here. P naught was this constant that I obtained by gathering the nominal load, the operating point, and this expression, which is K times the gain times what I had at the operating angle, right? So this is a constant that's characteristic, you know, that's determined by a combination of two things, the external load and the operating point. So I leave that in here. So from the equations of fixed, so I need to work on this a little bit, because yeah, this is it. I mean, if this is larger, if the left-hand side is larger than the right-hand side, then I'm done. But to gain more insight into the result, one can work a little bit on the equation for the fixed points, which is here. And you combine the equations, you find that for fixed points that P naught omega naught squared, which is this constant, is constant once you fix the remaining parameters. So your gain is fixed because you're not changing the controller. It actually, that gain comes out from the geometry. It's not an electronically implementable gain. That gain factor is in fact a function of your geometry. It comes out, it's just that there's no detailed calculation here for what that is. So all these are constants, the gear ratio and everything is constant. So from that perspective, these two vary, but the product of P naught times omega naught squared is a constant. So you can view omega naught as a function of P naught. So you can view the transpiring steady state spinning as a function of these constants. The load, essentially, this is a modified load because P naught is primarily the load, the deviation of the load from the operating point plus this other factor. So you can think of P naught primarily as something related to the load with a bit of modification and rescaling. So if you differentiate, if you then view this relationship as an implicit relationship for omega naught being as a function of P naught and differentiate with respect to P naught, which I have carried out here, using the implicit differentiation. First, this is a linear dependence on P naught, right? So in the first round, I just get omega naught squared, but then I keep P naught and differentiate omega naught squared with respect to P naught, okay? This is what I get then. And from this relationship, I get this derivative, the d omega naught d P naught, and I can express that. And this is instructive to look at because this is what measures sort of the non-uniformity of the performance, which means it measures the variation, the derivative of the operating speed of the fixed point with respect to changes in the load fundamentally. Because in this, if you don't tinker with your controller and you don't tinker with your desired operating point, all these are fixed, then it's really what in a given situation, what might change is the uncertainty is the load, right? Because it really depends on what a particular person using the steam engine for something will put on the other end, on the output side. So when you take that view, then fundamentally P naught fundamentally depends on the load, and this is the non-uniformity of performance, which if this derivative is zero, that means you have uniformity of performance, which means it doesn't matter if you tinker with the load, the engine is still spinning because it's incredibly robust. So you're putting very little load on the other end, right? So then the engine just basically being driven by the steam, and thus it has some energy loss, but fundamentally the load doesn't matter that much what that really is. Whereas if that derivative is high, that means that the engine is really reacting very strongly to changes in the load. And this is something that you want to pay attention to because it's hard to foresee exactly what the load will be in a given application of the engine. Long story short, if you then say you care about this, then you introduce this parameter nu, which will be just omega naught over 2 P naught because of this result. So I've taken the modulus of that because it's the magnitude of that matters. And then I can rewrite the condition for asymptotic stability by using that definition. And it really just comes down, look at this formula. And for 2 P naught over omega naught, that's 1 over nu. So the whole condition is just this. Damping, moment of inertia, mass, and non-uniformity of performance. When you multiply them all together, they have to be larger than 1. And here comes the interesting part. Because when you look at this formula, it turns out that all the things, technological developments and societal developments and everything in the Industrial Revolution was pointing, it was basically causing a failure of this criterion without people realizing it. So why is that? So that was this very insightful analysis by Vyshnegradsky. People wanted to build larger and bigger and better things. For that, you need bigger engines, okay? But if you start using bigger engines, this J, the moment of inertia of the engine, becomes larger. That's bad for, larger M. It's not the, I get to the moment of inertia. I misspoke. Larger engines simply larger mass. So when M is larger, then this number will be smaller, and you want it to be large. So using bigger engines is not getting you closer to stability, it gets you away from stability. So that was the first observation. What I mixed it up with is the increased operating speed, in fact. So you also want applications, general people, in which the engine is able to spin faster, But if the engine spins faster, it's okay to have a bigger mass because it's not the mass that will fundamentally determine the kinetic energy, since this is spinning machinery, but it's the moment of inertia J. So you better keep that down. So pick a mass distribution which is closer to the axis of spinning, and thereby you reduce the moment of inertia, even though you're increasing the mass, right? Otherwise, the forces that you are creating will be so large under the slightest eccentricity, which you will always have, right? That the whole engine will just rip itself off the bearings and stand up and walk through the house, right? And destroying pretty much everything. So you have to be very careful with rotating machinery and keep its inertia down and keep the eccentricity, moment of inertia and eccentricity small, right? So you naturally want smaller J. Again, if you then pick a smaller, more streamlined J, that's not good for stability because that will decrease this number. Also very interesting is this one. B is some characterization of the smoothness of the surface ultimately. So when you go back to the controller, that damping comes from contact between the various parts here, most notably here. People thought it was a good idea that, hey, we can do better now, we can do machining, we can actually come up with nicer, shinier surfaces. It doesn't have to be that rough. The minute you do that, you're decreasing the damping there in the system. And look what that does to you. If B becomes smaller, again, that's not good for your stability because that gets you closer to criticality and reduces your stability margin that you have, right? And finally, again, a natural need would be is that you're manufacturing steam engines and you don't want to have an infinite variety, but rather what you want to have is maybe finitely many different sizes, but then you want those to be versatile. So that means that even if the load changes different applications, that the engine should not be too sensitive to the change in load, right? Because then your customers will be happier. And that means that this sensitivity with respect to the non-uniformity of the performance should be reduced. So smaller nu means more uniform output, less dependence on the load. Once again, if you reduce nu, you're not doing anything good to stability. So look at all these things now. Amazingly, all these societal and technological developments, of course, they were occurring gradually and different engines, not all engines were changed in the exact same way, but they were both, or not both, all of them were basically pushing in the direction of instability, because maybe in this particular engine, you changed something a little bit, but still stable. Okay, so that was then a good idea to change, right? Next time, and maybe I don't even change that part, change other things. So you're basically inching in the direction of instability, and things are working until they start not working. And that's precisely what happened, is that at some point, all these changes start violating this condition because you're basically pushing this quantity down. It's no longer larger than 1, and then you start having problems. And of course, then people try makeshift solutions and try fixing them, changing the design without really understanding necessarily what they need to do. So I think this was really a major success story of mathematics. First time ever this qualitative analysis was done, even though it was done retroactively, but this showed the way how you can actually go ahead and design machinery to be comfortably in the stable operating state. And then it's no surprise that later on, when Stodola was starting to do systematic design for turbines, gas turbines, then he turned, I think that it was gas turbines, then he turned to Hurwitz, who was here in the math department, to have a systematic analysis, systematic tool. Now, the way I've done it here was not necessarily how Wisniewski did it, but this is how you would do it with the Routh-Hurwitz criterion. So, any questions? So again, this is essentially what happened, right? So you have 3 roots for this 3-dimensional system. And one of them is complex conjugates. In this case, the other one is real, as it turns out. And when you start changing the design parameters, they kind of move around, right? But if you change the design parameters as I have described them, very slowly they start moving. And for a while, nothing is happening. It's still stable. Now, when you start getting closer to the imaginary axis, it's still technically stable, but you will see larger, more sustained oscillations before they die out, right? So your engine that used to actually damp itself very quickly because of the controller, all of a sudden, it takes longer. So you see more vibrations, but the engine is still, you hear perhaps more vibrations. Fundamentally, the engine is still operating. But at some point, either this eigenvalue or typically actually these two cross to the other side, and then you get an unstable vibration. And that's a problem, because then it's growing amplitude oscillations and the engine is no longer under control, but it's losing stability. Any questions on this? If not, I'll go back to my notes. So here I'll copy this problem into my notes. But for now, I'd like to move on to the next subject in stability. And that's an alternative description, an alternative way to check stability and instability. And this goes by the name, very often, by the name of Lyapunov's second method. This is also due to Lyapunov. He was, I mean, this is, as far as I know, all this was in his thesis. I mean, not in its most general form, but all these ideas were there in his PhD thesis. So that's an incredible intellectual achievement. So let's talk about that. So this is chapter 7, and this goes by the name of Lyapunov's direct or second method. For stability. And you might wonder why we need another method to begin with, because this seems like a pretty efficient method. What is the method? The method is, one way or another, get information about the eigenvalues of the linearization in the fixed point, right? So the issues with that So I will be honest, I mean, linearization works in an amazing number of cases, but there are some in which there are some additional issues that linearization doesn't quite address. So the issues with linearization-based stability analysis. So it doesn't work when you have real parts of lambda I equals 0. But you cannot say either that in that case the system is necessarily unstable. It just it's not asymptotically stable, but it might be in a modus of operation that's still okay for your purposes. And in fact, in conservative systems, this happens all the time. It turns out that we talked about this before, did we? No, we didn't talk about, not in this course. But it turns out that in a conservative system, you cannot have, in fact, an asymptotically stable equilibrium point. And one way to, and this is something I'm going to talk about at more length in part 2 of this course, but if you have an asymptotically stable equilibrium point in the phase space, then it has a domain of attraction. And that means that all the trajectories then shrink down to the equilibrium point. So what used to be, say, a ball of initial conditions, over time, it will shrink down when time goes to infinity to an arbitrarily small volume. And it turns out that that's impossible to happen in the phase space of a conservative system or Hamiltonian system, if you will, because those also preserve phase space volume. So this is something that I'll talk usually about in the second part of this course. But already, if you look at the pendulum, which is the prime example of a conservative system, it has two kinds of fixed points, either saddles or centers. And it doesn't have any asymptotically stable fixed points. So the best you can hope for in a conservative system is a neutrally stable equilibrium point. And all those show up with 0 real parts under linearization. So real part of lambda I equals 0. When that's the case, that makes actually linearization inconclusive, but it nevertheless arises. So that's one of them. But tends to arise in conservative systems. And of course, you could say that real engineering structures are not conservative, and you're absolutely right. But there are areas of applied science in which people wouldn't even know how to model dissipation. For instance, molecular vibrations. You look at models of molecular vibrations, it's unclear what the source of dissipation would be. They are all conservative systems, very high dimensional conservative systems. Okay, so that they are relevant. And what I also find even more important, so this is number 2, which also affects us in the real sort of engineering world, is that, okay, you might be able to conclude that technically speaking, the fixed point is asymptotically stable. But what does that mean? It means that it's stable, which means small enough perturbations remain bounded, and it has a domain of attraction. How big is that domain of attraction is anybody's guess. And it might actually be tiny. And it might actually be so small that your perturbations that your structure will experience in its lifetime are actually much larger than that. So once again, it only tells you that there's some open neighborhood from which the trajectories decay, but you don't know anything about the size of that neighborhood. And that can be a problem. It is a problem. Let me give you an example. So linearization gives no information about the size of the domain of stability. One area where that actually has been a big puzzle, and I'll just say example, is transition to turbulence in pipe flows, in shear flows. Now, turbulence is described by the Navier-Stokes equation, which is a partial differential equation, but you can view that as an infinite dimensional dynamical system. And when you actually solve it on your computer, then you will discretize it, and it becomes an ordinary differential equation, which is of incredible size. But it's nevertheless, then in that case, the minute you really try to solve it numerically, you're no longer solving the PDE, but you're solving an OD, a dynamical system, a finite dimensional one. That's why it's relevant for this discussion. And you might remember from fluid mechanics courses that this has been a puzzle for the longest time, how pipe flows that are initially laminar transition to turbulence. You don't cause any perturbation, disturbance to the flow. You simply increase the Reynolds number, increase the speed, and you wait, okay? Until, and it's a laminar solution. The Navier-Stokes equation will tell you that for any Reynolds number, you will have the laminar solution. And if you linearize the Navier-Stokes equations, say, take a finite dimensional ODE approximation of it and linearize it along the laminar solution, you get the amazing result that it's stable, even asymptotically stable, for all Reynolds numbers. And that's what you actually observe for small Reynolds numbers. You bang on the wall of the pipe, and it's a long enough pipe so that it gives you some length of observation. Then maybe you cause a bump, but it'll die out. So the flow re-laminarizes. And then you increase the Reynolds number, you bang on it, it still re-laminizes unless the bang is really large, okay? Because then it might actually make you go to turbulence. But as the Reynolds number goes higher and higher and higher, for the longest time, people were reaching different conclusions as to at what point the flow turns turbulent. So, at what speed you need to reach for the laminar flow. And people had different conclusions, very high profile, Nikuradze, Reynolds, all these, I don't remember all the names, but I myself learned it in fluid mechanics, and they marked different critical Reynolds numbers for a while, and it was unclear why they were getting different results. And in fact, when you do a linear stability analysis, they should not be getting any finite Reynolds number beyond which this laminar flow loses stability if the Navier-Stokes equations are correct. So why were they all getting different results? So our current understanding is that the Navier-Stokes equations correctly predicts that the laminar flow is stable for any Reynolds number. However, the domain of stability is shrinking. And for large Reynolds numbers, it's tiny. And at that point, small differences in the experiments, roughness of the wall, length of the pipe, somebody's talking next to the experiment, a phone rings, these all tiny perturbations start making a difference and can make the flow go turbulent, because the domain of instability, the domain from which solutions actually decay down to the laminar solution, is so tiny that even though you're practically asymptotic stability within that, the perturbations are large enough at some point to kick you out of there, and then you go to turbulence. So to sort of just really, so transition to turbulence, say in pipe flow. And this is sort of the usual diagram. I won't do justice to it, but this is the Reynolds number, okay? So it's the Reynolds number of the laminar base flow. Which is really just this, right? So you have usual, say, profile, quadratic. You move in the pipe. Well, after, of course, that develops, whatever, irrespective of what initial flow you impose here, this classic profile will develop. So if we look at the amount of disturbance that makes you transition, so I'm going to measure it here, the norm of disturbance. Then what people usually report is a curve like this. And that means that, and it doesn't come back, so it comes down for the ideal pipe. So this is for the ideal pipe, which is basically as smooth as possible. And if you change the roughness of the pipe, then I think these, for low Reynolds numbers, these don't differ that much, but at some point they start changing. So you get these curves, the roughness of the pipe increases. The ideal Navier-Stokes approximation. So what you see here is when I say ideal pipe, but in fact the curve, I should say that this is where you have transition to turbulence. From a laminar flow to a turbulent flow. Okay, so here you have laminar behavior. You may actually have, I'm making this a bit oversimplifying, because there are regimes, for instance, you may have occasional bursts even in that regime, but then they kind of die out, right? And here, over that curve, in the case of the ideal flow, I'm showing this curve, here you have turbulent behavior. But that transition curve changes and in fact kind of levels off if you make the pipe more and more rough. So roughness, in fact, delays the transition. So for a real rough pipe, the norm of the disturbance kind of asymptotically levels off. Whereas for a very smooth pipe, and those tend to be the experimental pipes, this threshold actually keeps going down. And then in different experiments, depending on how perfect your experience is, when you're really close here, so the size of that domain of stability is really tiny, then even the smallest perturbation can put you on the other side. So this is roughly what you see here in the appropriate norm. This basically shows the size of domain of stability. And the reason, and again, because the base flow, laminar base flow, is asymptotically stable for all Reynolds numbers. That's the conclusion, at least from the Navier-Stokes equation. So you do linear stability analysis on the Navier-Stokes. This is what you get. So it was basically, people were giving too much credit for the linearization. Once again, it's technically correct, but the domain on which it's relevant might actually be tiny and it's shrinking down to 0. So now there's a pretty broad consensus that this is exactly what's going on there. And just because it's stable, it doesn't mean that you experimentally see it as stable, because your relevant perturbations are larger than that. And you can easily imagine mechanical systems. In fact, not long ago, we had Tobias Schneider here giving the SwissMech talk, in which he showed that when you look at bucklings of shells, there's a very similar effect there. In fact, he made the connection precisely because he has been working on turbulence. So there's a number of mechanical settings in which that is relevant. So it would be nice to have a procedure also that not only gives you asymptotic stability, but at least an estimate for the size of the domain of stability. Okay, and the Lyapunov second method has that ability. So let's. So this leads to the question: can we establish stability without linearization? And also, can we estimate size of the domain of stability? So the main theorem, again, is due to Lyapunov. And I will say that in advance that it's not a universal solution in the sense that it also assumes something. It gives you more, but it also assumes more. So we start with the same system that we considered before. So it's a first order dynamical system. And again, there are non-autonomous versions of this result, but let me just talk about the autonomous one. I will need f to be at least once continuously differentiable, but the variable can be n-dimensional. And I assume that the system has a fixed point at x naught. Okay, so therefore this is a fixed point. Okay, and here now I have to assume. For the linearization, I don't have to assume anything to conclude, because once I have once continuously differentiable assumed, then I can certainly linearize there, and I can take Jacobian and I go for the eigenvalues, either numerically or with the Routh-Hurwitz criterion, I can estimate the real part. So that would be I would be done in the linearized setting, but here I have to make more assumptions. And I have to assume that somebody actually gives me a function that is often available from physical insight or prior experience or by people, smart people constructing it. But I have to have a function given to me, which is defined on an open set around the fixed point of interest. So this function v has to be once continuously differentiable on this open set. So u in Rn is open. And x naught, my fixed point, is contained in u. Okay, such that here comes what I expect from that function. And I need to assume two things. Basically, I need to assume that this function is cup-shaped at x naught. Okay, so out of convenience, I can shift its values. If that's not the case, I can certainly achieve that it's 0 at x naught. So that's just shifting the graph of the function. That will play no role. It's more the shape of the function that plays a role. But as traditionally for the statement of these theorems, it comes handy to shift it to 0 because it's then easier to describe what I mean by a cup-shaped function. Namely, is that at all nearby values, it actually has to be positive in all of u except at x naught. Okay. So basically the picture that I have in mind is that here's the height of this is x naught, and I will measure x, the function in this direction, and I'm after a function that is somehow minimal. This is the graph of the function. This is the graph of v. And certainly this is the case on some subdomain, at least u. Of Rm. The function then reaches a minimum, which is 0. So here v equals 0 along this plane. But other than that, so it doesn't have to be quadratic. So this is a convenient way of saying that v is positive definite. In u. So the term positive definite, why go about it this way? Because we used the term positive definite before for quadratic forms, but I'm not assuming that this is a quadratic form. It's a general function, and I will call it positive definite if it reaches 0 only at this point, and then who knows what the shape of the function is, but in all other points in u, it's positive. Mind you, that it also involves functions that actually start growing and then keep coming back a bit, right? So it's not necessarily your classic cup, but it certainly becomes one near x naught. Okay, so all I want is that, and that's enough, is that in u, whatever it does, it cannot come down to 0 again. That's only the first assumption. The second assumption is that the derivative of this function along trajectories is non-positive. So v dot at the point x, which means that I imagine for a second that this is really x of t, one of the trajectories of the system. And when it's x of t, I plug in x of t into v, and I can then differentiate with respect to time. So using the rules of using the chain rule, that would mean that I first take the derivative of v, so it's the gradient of v, and then I plug in where I am right now, which is x. But then I have to multiply that by x dot, but x dot from my differential equation is just f of x. So I take this inner product of these two vectors. That's v dot. You can call that a definition, but this is the meaning of that. the instantaneous rate of change of V along the trajectory that right now goes through the point X, okay? And I don't want that to be positive, so it can be less than or equal to 0. Mind you that I don't need to know the trajectories of the system to evaluate this, right? Because it's instantaneous. There's no dependence absolutely here on the trajectories. I only assumed for a second that I know the trajectory for me to explain why I'm considering this. But then I can just say x of t right now is just x where I am. So this is a spatially dependent way of evaluating what the rate of change of v is along the trajectory that goes through that point x right now. Okay, and I require this for all x in u. Okay. So what that means, that the usual term for that is that IE, but not so thick. So IE, V dot, as we say, the derivative of V with respect to system, the system here, V dot is negative semi-definite in U. I know that V dot is 0 at the fixed point. How do I know that? Where at the fixed point, the right-hand side of the differential equation is 0. So if I happen to plug in the fixed point here, then this term is 0. So surely V dot is 0 at 0. But unlike V itself, I'm not requiring it to be negative everywhere else in U. I'm also allowing it to be 0 or negative. So that's why we're calling V dot negative semi-definite in U in exactly the same sense as we called V definite, positive definite in U. It's negative semi-definite. And then the statement is then x equals x naught is Lyapunov stable. Okay, and U is contained in the domain of stability, in its domain of stability. And that's a big deal, because that's a truly nonlinear result. So is the first one, because this is non-linearly Lyapunov stable, which we were never able to do before, because if we just talked about Lyapunov stability, which allows neutral stability, then linearization is never powerful enough to extend that to the nonlinear system. That's why we focused the linearization only on asymptotic stability. With asymptotic stability, we have the conclusion that it extends to nonlinear systems. But this is a more powerful result because it actually does not say that the system is asymptotically stable. It can actually be Lyapunov stable. And yet, at which point linearization has nothing else to say, because it's, sorry, inconclusive. This not only makes it conclusive for the linear system, but in fact for a nonlinear system, right? So that's a big deal. That's big deal number one. Big deal number two is that if this construct also tells me that this U set that I've been using in evaluating the conditions is a lower estimate for the domain of stability. In other words, all trajectories that start in U are ones that actually will be staying in there. Not necessarily in U, mind you, but they will be part of the domain of stability. They will be not growing away. Remember, there's the difference from here, at least. It's not clear whether this is, we'll see in the proof that how U relates to the actual domain of stability. But remember that the Lyapunov stability says that you are confined to some ball as long as you're starting from a smaller ball, right? So maybe U is just that smaller ball. I don't know yet. And maybe I'm technically leaving U, but the trajectories that start from U will be contained in a ball. So that's what I mean by being part of the domain of stability. We'll get to that when I get to the proof of this, because this is a nice geometric simple proof and it will then reveal the role of U. And that's what I'm going to do tomorrow, is just the one thing to point out that there's a big if in this. Can I actually, do I have a function like this at my disposal? And the good news is that in a number of problems, this actually function, this turns out to be the energy. So energy works very well as a Lyapunov function in a number of cases. And when it doesn't, then you may have ideas how to modify the energy, or what to add or what to take away to create a Lyapunov function that does work. And once you have these two satisfied, which does not involve again, any search for eigenvalues, okay, then automatically you get all this nonlinear stability and an estimate for the domain of stability. And one can even strengthen this further, as we'll see, to guarantee asymptotic stability. That's what you want. So I'll stop right now for this with this. And if you have any questions, I'll answer them. And if not, then we'll proceed with the proof of this tomorrow and other results of similar kind and examples. Anyone? So the end is important here. Nobody? Okay. No. Thank you. And see you tomorrow. Have a good evening.